In this lesson, we're going to simplify expressions with radicals and rational exponents. When we examined square roots earlier in the year, there were two things that had to be true in order for it to be simplified. The first was you would look at the radicand, and there could be no perfect square factors in the radicand. So if we're looking at a cube root function, we're not going to have any perfect cubes. Or fourth root, there can't be any perfect fourths. You also can't have a radical in the denominator of a fraction. If that's true, then we need to do that process where we rationalize the denominator. So let's begin by looking at something old, and then we'll apply it to something new. We've learned how to simplify the square root of 48. So one way of simplifying a radical is to break down the radicand into a product of primes. So 48 is 4 times 12, 4 is 2 times 2, both primes, so I circle them. 12 is 6 times 2, and 6 is 2 times 3. This is not the only way to simplify, but it's kind of a low-stress way. And what we do is we look for pairs, because our index on our radical is 2. So since I have a pair of 2's, we brought the 1, 2 on the outside. We look for another pair. I have another pair of 2's, so I would bring that out on the outside. And then I have this odd 3 left over, so that stays inside the radical. So I get 4 root 3. One of the things I always do then is I grab my calculator and I type in, you can see I've got the original and the answer typed in here that I simplified it to, and I make sure that my decimals match. It's a good way to check and make sure that you're doing everything correctly. So we're going to apply this concept now to radicals that are higher than just square root, where we do cube root, fourth root, fifth root, etc. So first thing I do is I look at the index on my radical. My index here is 3, the cube root. So I'm going to just zoom in here so you can see a little better. I begin by making my factor tree just as before. So factors of 135 would be 5 times 27. 5 is prime. 27 breaks into 9 times 3. And 9 into 3 times 3. Now, because I'm doing the cube root, okay, open up my radical, I'm looking for triples, or I need 3 of something, because the cube root of 3 to the third, in other words, would be just 3. So I see I have 1, 2, 3. So the cube root of 3 to the third, they undo each other, and that 3 comes out front. What's left over? This 5 inside. Again, grab your calculator and make sure that your answers match. So again, I've typed in both radicals, cube root of 135 and 3 times the cube root of 5, and I see that they're both approximately 5.13. All right, let's now simplify the fourth root of 80. So again, make your factor tree. So when I make my factor tree, this time I'm looking for anything to the fourth power. Okay, so I see 2 is there as a factor 4 times. So when I take the fourth root of 2 to the fourth, they undo each other and it leaves me with just 2. So the 2 comes on the outside, and the fourth root of what's left over, I have a 5, stays here. Again, please type both the fourth root of 80 and 2 times the fourth root of 5 into your calculator and confirm that your decimals match. Okay, let's go on and now look at what happens when we add in an operation. Previously in this course, we've looked at how to simplify products. Essentially, what we did was we multiplied coefficients together. So the coefficient on the first radical would be 1. So coefficients together, 1 times 15 was 15 times the square root, and then we multiplied radicands together, 2 times 24, which is 48. Now, if you have been taking notes with this video, a moment ago, we just simplified the root of 48, and we saw that that was 4 root 3. So I am not going to sit here and do it all over again. This would be 15 times 4 root 3, and then I just multiply 15 times 4 to get 60 root 3. Again, I highly encourage you to copy or to type the original expression exactly as you see it in one line in your calculator, and make sure that your simplified answer matches. Let's apply this concept now to higher radicals. So I have the 4 times the cube root of 12 times 2 times the cube root of 18. So I will multiply my coefficients together, and since my radicals have the same index, they're both the cube root, I can multiply my radicands together. All right, notice that condition I said that the indices have to be the same index. 4 times 2 would be 8 times the cube root of 12 times 18 is 216. Okay, now I'm going to simplify. So I'm going to break down 216. Well, I just saw that it was 12 times 18, so don't overthink that. Keep going. 6 times 2, 2 times 3. 18 would be 9 times 2, and 3 times 3. You should be getting quick at making factor trees. So since my index is 3, I'm looking for a perfect cube. All right, so what's something that's there 3 times? I see a 2. 1, 2, 3 2s. So that means a 2 is going to come out. And then I see 1, 2, 3 3s times 3. So nothing's left over. So that must have been a perfect cube. It was 6. So what I actually have then is 8 times 6, or 48 exactly. Again, please take a second, type that in your calculator, and make sure your answers match. All right, so number 4, fifth roots. And again, they both have an index of 5. So I'm going to multiply my coefficients together. Coefficient here would be 1. So negative 3 times 1 would be negative 3 times the fifth root of 2 times 64 would be 128. Now I'm going to break down 128. I just did 2 times 64 and then 8 times 8. Remember to go until every branch has a prime number on it. All right, so I'm looking for something with 5 factors since my index is 5. So is there anything to the 5th power? Let's count these 2's. It's 1, 2, 3, 4, 5 2's that I just highlighted. So that means on the outside I have my negative 3 times this 2, since there's 5 of them, the 5th root of that is just 2. Rewrite my radical. What's left over? Well, it looks like I have 2 2's inside the radical. So my final answer is negative 6 times the 5th root of 4. So you definitely need to do some practice with this. In the next quick tutorial, we'll mix in variables.